Okay, hi class. Today's discussion or this mini lesson will be on three-wire circuits, including the resistance on line conductors. So it's something that we haven't dealt with yet. This is an example of more of a real-life circumstance with three-wire circuits because we know our conductors have resistance on them, and how that conductor resistance applies to our installations within our homes will be dictated by the calculations that we run through here. The way that we do them is fairly straightforward. You just got to follow a couple of processes, apply your Ohm's law and your Watt's law, and solve the circuits appropriately. So the first example, we're just going to look at 1/2 of a three-wire circuit. This should be a review because we have done these before in line loss and line drop calculations. So if we start with 120 volts and we had 0.1 ohms of resistance on each of those line conductors, and I said that this load here was drawing 2 amps, okay, we could then assume that the 2 amps times the 0.1 will give us 0.2 volts there and 0.2 volts there. If we took the 120 and based on the current flow, subtracted 0.2 volts here and another 0.2 volts there, that'll give us with 119.6 volts out at our load. Okay, so that's the load voltage that we would see. All right, so that's pretty straightforward because that's just a line loss and line drop circuit. If we applied polarities to these resistors based on current flow, we would look, if we started up here, that's our true negative, so that's a negative there. Anytime we cross the load, we're going to get an instantaneous positive. This is negative, that's an instantaneous positive, instantaneous negative, and then there's our true positive heading back this way. All right, so we have voltage drops that occur within here. Now you'll see when we add a three-wire circuit to this circumstance, sometimes the neutral contains what's called a voltage rise, and that's based on our polarity of our current flow on that neutral if it's an unbalanced three-wire. So let's explore one similar to that right now. All right, so if we looked at a balanced three-wire circuit, still with our 0.1 ohms on each of our line conductors, okay, and I'm going to say that each of these loads is drawing the 2 amps. Because of the fact that each of those loads is drawing the same current, it's fair to say that our voltage draw, or our neutral, will not contain any current on it. We're going to start with a source voltage of 120 volts, okay. We're going to analyze the direction of current flow within here. And based on those arrows, we can apply polarities, like we did in the previous equation there. Okay, so that's our true positive. This is our true negative up there. Okay, no current flow on that neutral. So if we looked at our voltage drops, we could see the 0.1 times the 2, so we're looking at 0.2 volts here and 0.2 volts down there. All right. The difference here though is because there's no drop on the neutral like there was over in this one, our voltage drop across these loads is going to be slightly less than what it was over here. Okay, so we look at our entire source here. All right, we're going to go, or we could go, in this circumstance, we've got 0 volts here, okay? And if we followed almost like mimicking a current path this way, even though we have nothing on that, okay? We're going to look at this voltage drop out here would start at 120 volts, okay? And then we're going to subtract our 0.2 volts. So we're going to minus 0.2 volts, okay? And that gives us 119.8 volts. The reason why I didn't go any further is because we know our neutral's balanced. If there was current on that neutral, we'd have to take one more step, and I'll do that in a second. If we look at the next guy down here, we're going to start by analyzing potential for current flow there. It's a good habit to get into, to sort of break it into quadrants like this, okay? And we can start once again with our 120. And I guess we could technically say minus 0 volts because there's no drop there. And then we're going to minus the 0.2 here again to give us the same 119.8 volts. Okay? So that's in the case of a balanced 3-wire circuit. Now if we move over here to an unbalanced 3-wire circuit, things change a little bit. We're still going to keep our same resistance on our line conductors, same source voltage. Okay. However, I'm going to state that this load out here has 2 amps going to it, and this load down here has 4 amps going to it. Okay, so right away, because this load requires more current, we know that it's going to be, there has to be some current on the neutral. All right, so let's analyze how this would work. So we have our 2 amps up here. It's flowing this way, all right? But then we have 4 amps down here returning back. And just like we've done in previous, whatever leaves has to come back. So if we've got 4 returning and only 2 leaving, we have to have another 2 amps here, which is going to join into that 2 there to make that 4. All right? So now we can apply polarities, negative to positive, negative to positive, negative to positive, negative to positive based on that current flow. And I'm going to look here at a negative to a positive there based on the direction of current flow that way. Okay? Next, we're going to look at voltage drops. We've got our 2 times our 0.1, which is 0.2 volts again. 2 times 0.1, 0.2 volts there. And we've got 4 times 0.1, which is 0.4 volts here. All right, so now let's look at what voltage is going to be available at these circuits here. So if I did my swoops, like we did over on that, the one on the other board there, we're going to look at solving for our circuits based on the direction of those swoops. Why I started in the top left, that's where my current is coming out of up here. You always do it in that clockwise format, okay? And then that should help you solve what we're going to get into here. All right, so if we look at we're going to start with our 120 volts. We're looking at load 1 here, okay? So this will be E load 1 or V load 1, okay? Or I guess we could say R1 or whatever. But either way, start with 120, and then based on the fact that our swoop direction is going in the same direction as our current here, we're going to subtract 0.2 volts there. Down here is where it gets a bit interesting though, because our swoop is going in the opposite direction as our current flow. So technically, we're going to subtract a negative 0.2 volts there, okay? And anytime we subtract the negative, it would be the same as saying add, okay? And that takes us back to the source, so that's all we need to do. So we got 120 minus 0.2 minus a negative 0.2, leaving us with 120 out there. Okay, so this is what's called here. This is what's called a voltage rise within the circuit. Okay, now down below here, via load 2, okay, we're going to start with our 120 volts. And now, because our swoop is going in the same direction as that current flow, it's going to be a voltage drop. So we minus 0.2 volts. Okay, and then down below there, we've got another 0.4 volts. So we're going to minus 0.4 volts, which gives us 119.4. All right? That's pretty straightforward. Okay? So in this circumstance, this circuit, we had a voltage rise and a voltage drop, both on the neutral. It just depended on which side we were looking at. So you have to be prepared to solve for those. All right? And we'll do some further explanation on that in the Learning Hub. But that's a straightforward example of a 3-wire circuit using line conductor resistance into the equations as well. We need to look at the entire circuit, add our polarities to it, figure out our voltage drops based on current flow. If it's balanced, we know we don't have any current on the neutral. If it's unbalanced, then we have to take that neutral into consideration, and you're going to have their voltage rise and your voltage drop depending on which side of the circuit is unbalanced. Okay? So we're going to end this one there. I'm going to do a further one exploring a circuit like this with breaks across the neutral.